already heard. The title and the authors were read, so I will not repeat it because otherwise I will go over time most likely. Instead, I will straight go to motivation. And in a broad sense, a very broad statement that we can make is that execution of business processes relies on different types of information. Here, we are going to represent it as domain knowledge. This includes stuff like classifiers, ontologies, standard procedures, rules and regulations, and so on. Let's take some examples. And to think about those examples, first we have to realize that sometimes this information in our domain knowledge can be represented best as global rules, giving us, indicating the need for declarative modeling, but other times it is best represented as procedures, indicating the need for procedural modeling. So I mentioned already examples. Here is one. It tells us that amoxicillin and varafin cannot occur in the same case. These are two different types of drugs, but when you administer both of them together, then there is an increased risk of internal bleedings, which we kind of want to avoid. But we don't have only declarative approach or only declarative specifications, but also procedural. This would be our standard procedures. So standard treatment of venous thrombolism is something that I will use here as an example. In this specification, we have an intervention decision, and based on the decision that is going to be made, we have 3 different procedures that will follow. So let's take a look at those models in a bit more detail. First of all, we can already realize that the information in those specifications, it can overlap. In this case, we have varafin treatment, which occurs in both of these specifications. Now, ideally, such overlaps are going to agree on what is the next best course of action. There won't be any conflicts. The models play nice together, and everything is beautiful. Unfortunately, we do not live in an ideal world. So, for example, let's say that we have a patient where we have made the intervention decision saying that varafin is going to be administered. And now, let's say that we actually find out that this same patient has also peptic ulcer, so we have to follow another standard treatment procedure at the same time to treat all the health problems that this patient has. Now here, the thing that happens is that depending on the results of the HP evaluation test, which is the first activity in this procedure, we can end up in a position where the procedure or the standard treatment procedure requires us to also do amoxicillin treatment. And now we are in a position where we basically have a 3-way conflict between the specifications that we are currently following. So how can we handle these situations? Well, the obvious answer is, of course, or the first thing that comes to mind is that what if we just try to model the processes better? Let's handle everything at the modeling level and everything will be beautiful again. Well, unfortunately, we have to think of some problems. So could there be inherent conflicts in the best available domain knowledge? I would argue yes. Even on Monday, we heard that if you're going to put 5 doctors in the same room, you'll get 5 different opinions. So it might be the case that even we don't agree what is actually the best available domain knowledge in some cases. Another thing is that could we really handle all potential situations reliably? Think of all possible comorbidities that can occur while treating a patient, combine all of that with all potential allergies that a patient may have, all severity levels of those allergies, and so on. The state space of what we need to consider becomes inconceivably large, especially if we want to fold all of this behavior into a single process model. Should we even try something in terms of modeling processes better? Of course. I am not advocating here for sloppy modeling or anything like that. Let's try to make our models as good as we can. However, bear in mind the complexity issues that we can run into, such as the infamous spaghetti models that we can have from process mining when we find actual process executions. And this, by the way, is a very light example because here you can still distinguish the different lines, but in practice it can go much more complex. So what can be the alternatives? I will present one of them, but of course there can be some others as well. Mainly I'm interested in the perspective of monitoring for this presentation. And what I have in mind is this. First, we are going to model the domain knowledge in fragments, choosing the best representation for each piece of information. Then we are going to combine the models based on the incoming case. Support the process execution now through monitoring. So we are going to make monitoring the integral part of actually carrying out the process. And this is going to be based on the case-specific combination of the models. In doing so, we have to guide the process workers at each step of the process. We have to warn them about potential future conflicts and also provide on-the-fly support for conflict resolution as necessary. And now this is nicely going to lead into the main part of the presentation, which is multimodal monitoring itself. Now, for the purposes of multimodal monitoring, we have the main contribution of this work is the M3 framework. The M3 stands for multimodal monitoring, so you get 3 M's nicely. And here I'm going to start to build the monitoring framework step by step, leading up to the main figure of the paper itself. And we will start with something that is already familiar, domain knowledge, classifiers, standard procedures, and so on. However, if you want to execute processes in practice, then domain knowledge alone, I would argue, is not sufficient, and we actually have to consider also organizational context. So this would be our business priorities that we set in our organization, but also the available resources. Even if the procedures that we follow are exactly the same, then the available workforce is going to be different from one hospital to the next. And this leads us to the first phase of our framework, which we call the elicitation phase. To understand what it is, let's switch to a different slide, and let's go step by step. First of all, life cycle. We consider it a continuous case-agnostic phase, meaning that it is a phase that is carried out continuously in an organization, regardless of the incoming cases. The purpose here is to ensure up-to-date process specifications, and it has multiple steps. 1, extraction. This is what we refer to when we want to gather up all the available knowledge. So what are our resources, what are the regulations that we are following, what are the standard procedures, and so on. Once we have all that knowledge gathered up, we actually have to do something called harmonization based on classifiers, ontologies, and so on to make sure that whatever information we have, it speaks the same language. For example, that amoxicillin treatment is always denoted by the label AT. Here we can rely on different classifiers, loin codes, whatever. There are many different ways how to do this. Then we come to the modeling step, where we are going to figure out which pieces of knowledge are best represented declaratively, which procedurally, what are the best notations, and so on. And finally, we are going to produce the models themselves, and we are also going to give them priorities, because every process, all process specifications are not equal. Violating one might have very serious side effects, while violating another might be, it happens. So we kind of have to think about what is the importance of the specifications that we are dealing with. And of course, we need a place to put them in, which in our case is specification repository, also going to be connected to the extraction step and harmonization step. So now I can go back to the M3 framework itself and add in the specification repository as well. Here we also have the declarative specifications, procedure specifications, and specification priorities. But of course, this is not the entire framework. However, if we have already this, then we can start thinking about incoming cases. So let's add an incoming case. And this is going to lead into the second phase of our framework, which we call preparation phase. Here, as before, I will switch slides to go into a bit more detail. First of all, again, life cycle. Here we consider this phase to be non-recurrent, case-specific phase. So it's based on the characteristics of incoming case, and it will not be repeated for the same case again. The purpose is creating a hybrid specification for the case to be monitored. And again, multiple steps. All of them, or not all of them, but some of them is based on the specification repository itself that I mentioned before. First step, we are going to have the incoming case, as I mentioned before, and now we have to assess this case to figure out what are the actual relevant pieces of knowledge that we need in order to execute this or carry out this case successfully. Based on that assessment, we are going to get a set of relevant process specifications, and we can lead into or move into the next step of fine-tuning. Now, this step is optional, but it's here because we cannot assume that we have, even if we do it in fragments, we still cannot assume that we have modeled absolutely everything that we can possibly encounter in real life. So you need a step where you can still do some optional modifications or add in new knowledge. As a result, we get a set of custom specifications, both of which are going to be used for the purposes of automated assimilation. And this is a step that is going to be done automatically. It's going to take both the relevant specifications and custom specifications and produce out of them a hybrid specification, which then is going to be the basis of further monitoring steps. Now, this allows me to go back to the framework slide itself and add into here the hybrid specification that I just mentioned. And now once we have the hybrid specification, then finally we can begin with the monitoring phase itself. This is going to be based, of course, based on the hybrid specification and also an event stream. But how it works, again, switch of slide, and let's take a life cycle first. It is ongoing case-specific phase. The purpose here is to support the execution of the process instance from beginning to end. And to do that, we again rely on the specification repository in part, but the main steps themselves are taking the hybrid specification, taking the events that are occurring in the event stream, and then we go event by event, automatically processing each event. And out of this processing, we get monitoring status, but also activity recommendations. Based on this, there is, of course, an optional step of case reassessment because, well, unexpected things happen in life as well. Once this is done, we go to the next event execution based around the activity recommendations and monitoring states, which is going to feed back into the event stream itself. And now I can go back and add in the final piece of the framework itself. And this is kind of the full framework and the figure that we have in the paper as well. One thing to note here is that the monitoring status is actually going to give you information about global conflicts that can occur in advance even. It can give you information about which specific process specifications are going to be violated and so on. And activity recommendations, it can be a set of activity recommendations because sometimes two different activities, well, they are kind of equal. You can do one or the other before. It doesn't matter sometimes. But I realized that this talk, or this part, has been fairly high level and conceptual. So I'll be a bit more concrete now and go to the current implementation. We have some parts of this framework implemented, but not everything. More specifically, we have done a prototype that supports declarative specifications by relying on multi-perspective declare with local conditions. Additionally, it supports procedural specifications which rely on data battery nets with read and write guards. Of course, we have the specification priorities, which we are currently handling just as positive integer values. The higher the value, the higher the priority of the specification, and in turn, the higher the cost of violating that specification. And we can also build the hybrid specification itself, which in our current implementation is technically a guarded finite state automaton, which I will be discussing briefly on the later slide. But before that, we also have core algorithms, which support from the framework the preparation phase, leading to the hybrid specification itself, and also the monitoring phase, including the monitoring status and activity recommendations. One thing that you will note here is that the specification repository is not missing from this part of the slide. This is because we haven't yet figured out how to do it, and this is something that we will look at in future works. Now, I promised to talk a bit about how the guarded finite state automaton itself works, but before that, I have to give like a conceptual understanding of how this entire construct that we have, how it actually fits together and how the monitoring on it looks like. So one case, or you can think of it in such a way that one case goes through multiple local processes in parallel. So all of those processes apply to the same case, but at the same time. If you think of it like this, then what we came up with is that common activities So the activities that are mentioned in multiple process specifications, those are executed synchronously, meaning that if two specifications tell that I have to get an antibiotic shot, then I will not get 2 shots, but still 1, satisfying thus both of the specifications that require it. Then, not known activities, because if we have individual specifications, then it's quite likely that one specification is not going to cover all activities that are mentioned in other ones. This means that in our case that, for example, as a battery net is going to be modified slightly, such that it's going to ignore all of the activities that are not part of the alphabet of that battery net. And each local process has its own data and conditions, meaning that one battery net cannot interfere with the written variables of another battery net, for example. Some other things that we have to think about is how to capture cross-process requirements. In our case, what we are using here is the satisfaction of global data-aware constraints, coming to the MP-declare part that I mentioned before. And we also have to think about how to capture the desired end states of the global process, so the combination of everything that we have. And in here, we rely basically on the final markings of the local data battery nets. This, in other words, means that if a battery net is included in monitoring, then we assume that all the activities mandated by it have to be carried out until the final marking has been reached. If the process stops before that, then we consider it a violation of that battery net. And finally, and most importantly, actually, we should accept in our situation that violations and conflicts are always a possibility. This is something that even if we try our best, I think we cannot get around simply by modeling things better. So we have to realize that violations can happen, conflicts can happen, and what is the best way of dealing with it. In our case, what we figured out is that execution is going to continue even if one local process is violated, because we can still rely on all the non-violated local processes at the same time and still provide valuable input to the process workers. Now, I also promised to mention the hybrid specification. We have an upcoming formalization about it as well, but it's not covered in this paper, so I will not go into too much detail here. But in general, we rely on an automata. I'm assuming that most of you are going to know what it is. You might know it as a state machine as well. What we use here, basically it's a set of states and transitions connecting these states. In our case, we label the states with the activity names. And here, for simplicity, I've used the same activity names that we had in the earlier example, but in practice, we are going to translate them into propositionalized events, because this allows us to handle data perspective as well. More specifically, we are going to encode the activity name, relevant data payload, and written variables for each possible event. We refer to them as event signatures. And the data perspective, including infinities that can happen, are handled with interval abstraction. So maybe I've just briefly mentioning, infinities here means that if you have a condition saying x greater than 5, then what you actually have is an interval from 5 to positive infinity. And you can actually treat it in, if you do things right, you can treat it as a single interval. Then the states themselves, they are annotated with some information. One of these is monitoring status for each input specification. So no matter which state our process execution is in, we can always quickly look up what is the monitoring status of each individual process specification that we are working with. And second, cost of stopping and best reachable cost. These require a bit of explanation as well. Basically, cost of stopping means that if process execution stops right now, then what is the total cost of violations that we are going to incur? Meanwhile, the cost or the best reachable cost means basically that if we play our cards right, we do all the correct executions or all the correct events, then what is the best case scenario that we can reach from the current state? As an example, I have marked one of these states, and based on the information that we have, we can see that if we are in the state, we have 2 violations if we stop right now, And the next best course of action is the event named PU-EV. Now, given that I'm already over time a bit, I will just mention briefly something about scalability. One, the prototype has the memory requirements of prototype of the current prototype implementation are quite high. So scaling is something that we have to deal with. But on the other hand, performance during monitoring is very good. So all the individual events, they are processed practically instantaneously. And for future work, I think I will just click through them and leave them up for your reading pleasure until questions arrive. So thank you very much for your attention. And that's it.
The microphone is restarting. Questions in the meanwhile?
Software is fun.
Thanks, Antti, for a really nice presentation. Let me see if I understand correctly. So if you go back to the executional model, there was something about local models. And local models are sharing also global activities between each other, right? Mm-hmm. So wouldn't you have some further guarantees regarding the state of those sharing ones? Because in the end, what you have there is basically a set of LTL formula. And okay, so let me say it again. So if you have a network of declare models that are sharing some events, somehow the state of those events that are shared somehow need to be the same. Otherwise, you will end up with some ambiguity there. Do you need to guarantee that?
If I understand the question correctly, then I think I don't, because at least in our experiments, we haven't reached any ambiguity, especially with declare, because the declare itself is kind of designed in a way that allows your constraints to be, compositional, meaning that you can always add one more constraint on top of the existing model and it should work out unless you introduce some logical inconsistencies.
Yeah, but you're executing it locally, right? So you're executing one local model at a time, and then the synchronization goes on the other side.
Okay, I see where it went. Maybe I have to go back here. So this is actually the data structure that we are going to base our execution on. Mm-hmm. So this is basically what we do. We take the declare constraints. We build based on the LTL formulas underneath. We build the finite state automata, and finally we do the cross product. So we get the entire combination of those. We are not going to minimize it because we want to also include the situations where one part of the model is violated, but other parts are still not. So we basically do it by doing the cross product. We are kind of merging everything into a single data structure, and we can do the monitoring based on that.
Mm-hmm. Okay. Thanks.
Absolutely.
Other questions? Okay. Then I have some questions.
Yeah. Actually, I have two but related questions. I think the second question you already answered partially by having time in your future work, because it seems that a lot of your assumptions are actually time dependent. So that you, for example, that you should not take two drugs, that usually means at the same time. Mm-hmm. And so one of the solutions would already be to shift some treatment, and then you avoid conflicts. This is currently not represented in your
model. This is currently not represented. Currently what we are basically doing is, in each situation, we just say that the two drugs, they cannot occur in the same treatment case. So throughout the entire thing, but you are absolutely correct. Actually, it would be far better to include the time perspective as well, because if your ongoing treatment case is half a year, then does it really matter if it's one drug in January and another one in June? Like the time distance is so long, then it shouldn't be considered a conflict, actually.
And the other thing is you identify, let's say, global activities which appear in each local process. So your example was with the with the antibiotic shot. But there are also things which you have to repeat. For example, you need a lab test, and for that you need blood. But if you have two different lab tests, you need more blood. So they're influencing each other. You can't just factor them out. Can you represent this difference?
Let me think for a moment. I think it should be possible, but we don't have it in our implementation at the moment. I think it should be possible because it kind of boils down to modifications of the automata that you are going to use for the individual specification. And it also relates to one of the other future works in here, which was about the recovery strategies, because it's also the case that if you violate some constraint once, then a month down the line, that same constraint might become like relevant again. And this is also something that hasn't been handled here. And one of the things that I still have to add to this question is that you actually touch upon something that, in my opinion, is like a wider topic in general, because if you are dealing with multiple models that are executed concurrently, especially Petri nets, because they are not designed to be used in such a way, actually, then you have to figure out what are the combined execution semantics, like how the entire system together works. Now, what we have at the moment, we have defined some set of semantics of how the system could work. But it is entirely possible that in future research, we might modify these semantics. At the moment, we went the way that we took those rules that made sense to us as experts. But this doesn't mean that we have covered every possibility that is out there. So it's kind of, I think, a future work, and in my opinion, quite a wide piece of future work. Marco wants to add something.
You had the question, right?
Can you give it to Marco?
You want to comment, Marco? I just wanted to comment. Wait a moment.
So actually, Johan, these are all very interesting points. I think Antti already replied completely from the conceptual perspective, but just to add a bit of formality. So one interesting aspect that we could notice, at least, is that all these techniques that we use to handle the data perspective, they tend to be orthogonal with aspects like quantitative time or time intervals. So if you have techniques to tame the complications that arise when you want to move to richer models of time, typically they compose well with these data abstraction techniques that we use, which is a good indication to extend this, right? The second relates to, for example, these additive constraints. Part of this we could handle through the data variables. There is a whole part that Antti obviously could not focus on here, is related also to the talk I have later today. In these data Petri nets, you can have very different constraints, right? So you could start having arithmetics, and if you start having arithmetics, some of these additive aspects you could model there, right?
Question, right?
Yep, there. The exercise continues.
First of all, thank you very much for the interesting presentation. So I was wondering whether the GFA already includes the DPN, or is it made compatible with the DPN at runtime? And then, if so, you basically say that you want to also elicit the most relevant bits of both representations. So then can you do this by using different GFAs to select whether, or like see which ones have, let's say, the least violations throughout? Like, can you make this into some sort of a like model composition framework that makes like the nicest model in a way under certain conditions?
What do you mean by nicest?
Like in terms of the fewest violations, or for example the best compatibility, or like the least overlap in between the representations, because
okay.
Is it really nice to have two different representations?
Okay, there are multiple questions here. I'll start from the end then. Is it nice to have multiple representations? I think, in my opinion, I don't think it's a problem as well, as long as we can handle it. And this, in this specification is, or this framework, this is exactly what we want to do. And yeah, I don't think this is a problem. Now, you mentioned the guard finite state automata itself. I didn't get into the details of how it's actually built, but I'll mention just briefly what we basically do, especially for battery nets. We don't, well, the first step is we actually have to unify the alphabet of the battery net with all other relevant specifications. It has to speak the common language. The way to do it is simply you add a simple one transition into it that does not have any inputs or output places, so it can fire always, and you label it with all the activities that are not part of this battery net, but belong to other process specifications. Then, based on that, you are going to calculate the reachability graph of the markings of the battery net, and this reachability graph actually can naturally be represented as an automata. And then when we get to the guard finite state automaton part, this is where we kind of combine all the automata that we actually have. Yeah. And the niceness part, or the eliciting, like the model that fits all of those, like the combination, I haven't considered it from the perspective of producing an actual model that you can view in your favorite model editor. But what I can tell you is that if you have this construction here, then producing traces that actually match like the entire set of specifications that we are working with, actually it becomes kind of trivial, because at each state of the automata, you can just follow the best reachable cost. If there are multiple ones, you pick a random one, then you can generate positive traces. But if you want to do it in another way, then you take all of them and you draw the process map based on that. So technically you could do it, but I'm not sure how nice it would look. I think it would be too big.
Yes, so this is kind of a compound question related to the question of complexity, basically. So one of the things I'm looking, because my understanding is you're mainly looking at monitoring at this point, isn't it? Yes. So my question is really, do you really need those automaton, especially if you've got like hundreds of instances going concurrently? You're dealing with a state explosion if you want to have a static finite state machine. I mean, so what are the advantages you gain from using that state machine? And maybe would it be useful to do an ad hoc state machine from a given state? So if you are in a state, you're monitoring now, where can you go?
Yep.
It has a lot less states because there's a lot already known.
Absolutely, absolutely. No, the question you mentioned about like the scalability exponential complexity, you are absolutely right. This is definitely something that is going to happen because we are like building cross products of automata. This is in and of itself is kind of complex thing. This is also the reason why we have the memory requirements that we have. Secondly, I think you are correct that we should indeed look towards ways of doing it more intelligently. And this is actually what I mean by the on-the-fly automata construction here. Okay. So this is one of the options that we have for future to see if we can actually build the automata at runtime, like smaller piece by piece, let's say, as the process is evolving. So we wouldn't have to do the full specification because that, well, takes a lot of memory, for one thing. And yeah, that is basically where we want to go. But I will end the answer with this. At this stage, the reason why we actually did it like the full cross product was that we haven't seen any works that actually try to do concurrent monitoring of like multiple process specifications. So we wanted to have a working prototype that we can play around with, even if it's not optimal. Yeah. We wanted to see if it actually works and if it's something worth pursuing. And yeah, finally, I think indeed, the current approach is something that we have to improve upon in order to make it actually applicable in practice.
Yeah. Yeah, so I mean, to me, one of the advantages I see actually, it's more of an intuition, so is the idea that you can actually determine that you have already made choices that are hidden that might actually invalidate the process in the future.
Yeah, that's true.
And if you just look locally, okay, what are my constraints now? You'll find that actually later, where you actually might already find that you're in a sink.
That is,
if you model it fully.
yeah, that is actually absolutely true, because in this example, it is entirely possible that you get into a position where the best reachable cost from a given automaton state is 5 or more, but all the individual process specifications are still satisfied. They are fine. But you have made some decisions that lead you down the path where you are going to eventually violate something. So that can instantly happen. Okay. Did Marco want to add something?
There are other questions. No, Marco wants to say something.
Oh, yeah, just wanted to reinforce what Antti replied. So all this interplay that leads to this unique automaton is to be able to reason on the possible futures, which here is to foresee violations or the possibility of repairing to violations, but also to do this optimization based on the priorities. If you want to give that up and just monitor prefixes, so the trace you collected so far, then you can forget about this and just monitor each single piece separately, which is much more efficient, obviously, right? But does not give you this ability to reason on the possible futures.
I have, if I can, asking for 1 minute more to the audience, a very last question. If I got correctly, you are making the monitoring, but also a little bit of enactment of the processes that you are dealing with. Or I understand wrongly. What I want to do is that when you do monitoring, we have an execution system that is the one in charge of executing the process. In your case of the medical will be mobiles or IoT devices in which the people take the pills and so on. These generate events that your original figure are the event stream, and then you have your monitoring system on the other side that does all the reasoning that you proposed. So I would like to understand the interaction among these two systems, or how do you envision to have it? So how do you assume that the event stream will reach your system and the prediction that are done by your system will get back to the real enactment system of the process?
That is a good question, and I don't think I have a well thought out answer for this at the moment, because, well, the framework is, I would say, at a conceptual level where it still can be modified quite a bit. So it kind of boils down to, it's actually relates to this part. So what are the steps necessary to actually integrate this approach into an organizational context? And this is something that we haven't looked at yet.
But in your current prototype, you say that you are in M3. How do you assume that the event stream will be coming?
In my current prototype, what I'm doing actually for the experiments, I am using a pre-existing event log, processing it event by event. After each event, I'm producing the activity recommendations, and during the execution, I don't look into the future.
Okay, clear. Thank you.
Okay, thank you.